Here we've got a fluid that's flowing through a bend in the pipe, and it enters at location 1 at a speed of 10 meters per second. It leaves at location 2 at a speed of only 5 meters per second. Because of that, because the fluid slows down and because it's incompressible, this means that the area of surface 2 must be greater than the area of surface 1. This is because the mass flow rate at 1, the mass flow entering, has to equal the mass flow rate leaving at location 2. And that means that we've got the density multiplied by the velocity v1 multiplied by a1 is equal to the density of the water multiplied by v2 times the area at 2. Because the water is incompressible, its density is the same at both the entrance and the exit, and because v1 is larger than v2, this implies that a2 must be larger than a1. And we can observe that here, the area of 1, the diameter at 1 is smaller than the diameter at 2. And the question we've got is to calculate values for u1, u2, v1, and v2, along with the dot product v1, n1, and v2, n2. And we need to be careful not to make any sign mistakes here. Well, let's start by decomposing v1 into its horizontal and vertical components. So the horizontal component there, and the vertical component acting in the downward. We'll have to be careful that that is a negative quantity. So the magnitude of this vector represents u1, the magnitude of that vector represents v1. We know the angle of the pipe. This angle here is 30 degrees. That means that this angle is also equal to 30 degrees. Doing some trigonometry, we'll find that u1 is equal to the magnitude of v1 multiplied by the cosine of 30 degrees. Plugging in numbers, we find that u1 is equal to a positive 8.66 meters per second. Similarly, v1 is equal to negative v1, the magnitude of v1, being careful with the signs, multiplied by the sine of 30 degrees. And that's equal to negative 5 meters per second. We can also decompose, similarly, v2 into its horizontal and vertical components. In this case, the horizontal is to the right, and the vertical is upward, so both of these, u2 and v2, are going to be positive quantities. And we know the angle of this vector from the horizontal is equal to 60 degrees. So u2 is equal to the magnitude of v2 multiplied by the cosine of 60 degrees, and that's equal to 2.5 meters per second. Similarly, v2 is equal to the magnitude of v2 multiplied by the sine of 60 degrees, and that's equal to 4.33 meters per second. Both of these positive quantities. The next thing we need to calculate is v1 dotted with n1 and v2 dotted with n2. Well, let's take a look at the side of the pipe here. Zooming in on that, we know that the fluid is entering normal to that surface. So we draw the velocity vectors here. This is v1 coming in at that location, and then the unit normal points opposite to v1. So examining this, v1 dotted with n1, from this perspective, v1 dotted with n1 are opposite. The angle between the two is 180 degrees. So we'll find that v1 dotted with n1 is equal to the magnitude of v1 multiplied by the magnitude of n1 multiplied by the cosine of 180 degrees, which is equal to negative 1. So we would find v1 dot n1 is equal to negative magnitude of v1, which is equal to negative 10 meters per second. Similarly, we can examine the part of the pipe where the fluid is exiting, and we'll find that v2 dotted with n2, for the same logic, is going to be equal to the magnitude of v2. And this is because v2 and n2 are pointing in the same direction. So by definition of the dot product, cosine of 0 is equal to 1, the magnitude at the unit normal is equal to 1. We'll find v2 dot n2 equal to the magnitude of v2, which is equal to 5 meters per second, a positive quantity. So filling them in here, v1 dot n1 is equal to negative 10 meters per second. v2 dot n2 is equal to positive 5 meters per second.